Hello and welcome to my presentation on the Enigma cryptography system. In this presentation, I'm going to go over an overview of the history of the Enigma machine briefly, as well as its inner workings and how the actual encipherment of the text worked. I'll also show a brief demonstration of a simulation of the Enigma machine written in Python, both encoding and decoding text, as well as how the Allies managed to break the Enigma code in the war. So, a brief history. It was invented by Arthur Scherbis in the 1920s for commercial and banking purposes. The original units, of course, were extremely simple, in contrast to the units that were actually used by Germany in World War II. They had a very small key space of about 17,000 possible initial configurations. The machine itself looked very much like a typewriter that also had a backlit display that showed several letters, and the way that it would work is that if you wanted to encipher a message, you would type it out on this typewriter, but you would type it one letter at a time, and each time that you would type a letter, it would light up a different letter on the backlit display. So, for instance, if I were to press the A key, it might light up I. Now, it's difficult to predict which one it would light up because it used a polyalphabetic substitution that was completely periodic. So every single time that you would press the key, a new substitution table, if you will, would be generated. And what that substitution table would be was determined by the rotors at the top of the screen. Here is just an image labeling these different parts. So, of course, we have the keyboard. It looks like a standard typewriter, and then just above it, you have your backlit display to show, the enciphered letters. Or if you're deciphering the text, it would show, what letter you pressed and represented the letter in the plain text. And then up at the top of the machine, you can see the rotors. It's difficult to see in this picture, but each rotor has a letter label. So each rotor, by consequence, has 26 different positions that it can be in. And this is going to be important later when we start to look at exactly how the machine works. The original machine did not have the plug board. The plug board was added by Germany in World War II to increase the complexity of the system. But we'll go over more of that later. Now, looking at the rotor system itself, we know that this is a polyalphabetic periodic substitution, and the rotors were how this substitution was handled. You can see here from this diagram that we have the square letters represent a key that is typed in, and the red line represents the path of the electrical impulse generated by typing that key. And the path would travel through a number of different pathways. It would go through the right rotor, into the middle, through the left, and then it would turn around and come back through the rotors again, and it would be output to a certain lamp. Now, every time that you would press a key, the very rightmost rotor would advance one position, which would completely change the path that the signal would take, and hence would completely change the letter that would light up on the other side, as you can see here. As I mentioned before, this simple rotor system enabled roughly 17,000 possible states for the machine, possible substitution tables, as I mentioned. This, even by the standards of 1920s, 1930s, was not a very strong system, because someone who was persistent enough could sit through and just work through all of the settings until they found something that would produce meaningful output. The Germans, of course, recognized this, so they beefed it up substantially, and we'll go ahead and go through some of the improvements that they made to make this system much more viable. Now, one thing that they did was they made the points at which one rotor would cause the next rotor to rotate variable. And just to get a picture of that, like I said before, whenever you would press a key on the Enigma machine, the very first dial would rotate. Well, at a certain point, once that first rotor got to a certain position, one of the 26 positions that was available on it, it would cause the next rotor in the sequence to rotate, which gave you that total of 17,000 initial states, because it'd be 26 positions for the first rotor times 26 positions for the second rotor times 26 positions for the third. Now, by allowing the rotors to trigger the rotation of the next rotor at any given spot on the wheel with these ring settings, it increased the number of possible initial states by a factor of 676, which is quite a bit. Another thing that was done to increase the security of the Enigma machine was that, well, in the original machine, the rotors were fixed in place. They couldn't be taken out, they couldn't be moved around. So the Germans made it to where you could actually take the rotors out and you could swap the places. So instead of having the original rightmost rotor over on the right-hand side, you could take it, you could put it at the end, and that would generate a completely different set of substitutions. So given that you had 3 rotors in 3 places that you could place them, that gave you an additional 6, a factor of 6 that you could generate as far as key space. So you multiply, 676 times 6 times the 17,000 earlier, and that gives you, your key space now with these improvements. Another very large improvement that they made, they created 5 alternate rotors. So now instead of having 3 rotors that would go into 3 positions, you now had a total of 8 rotors that could go into 3 different positions, which multiplied this number of initial positions that we could have by an additional factor of 56. After all of these improvements had been made, the key space had gotten up to be about 4 billion, which is roughly equivalent to around a 32-bit key in modern standards, which is pretty outstanding. But the Germans did not stop there. They implemented the plug board, which was it's very simple in its design, but it is wickedly it introduces an enormous amount of complexity to this problem. And this is because of the sort of factorial nature by which letters can be paired. So what it would do is it added this additional layer of scrambling to the cipher. So let's say you press the A key on the Enigma machine. Well, before it would go to the rotors, it would check and it would see if, in this picture you can see that A is connected to the letter O. So instead of sending the letter A, so the signal for the letter A through the rotors, it would send the signal for the letter O, and then it would do the transformation for the letter O, which just, again, it introduces that additional step that makes the Enigma have several more initial states available to it. It keeps you guessing on, exactly how the substitution will work. Because if you knew the rotor settings and the plug board settings that you had were not correct, it would still give you completely useless output unless the plug board was correct because of how everything was routed. So the plug board itself introduces a factor of 150 trillion different combinations, different ways that these letters could be paired. Because as you can see, the cable will connect one letter to another letter. And usually there would be about 10 letter pairs for a total of 20 letters being connected at any given time. And this was quite common for there to be that maximum of 10, yielding this possible combinations of 150 trillion. Multiplying that by the previous 4 billion leaves us with an absurdly large number, which in scientific notation is about 6.02 times 10 to the 23rd, roughly equivalent to an 84-bit key by today's standards. So let's have a look at an actual Enigma machine simulation written in Python. This simulation is directly equivalent to one of the World War II era M4 Enigma machines that was used by the German Naval and U-Boat Command, and it's considered by far to be the most secure version with the largest key space. And we'll start out running it by doing the Python command, and we'll use Enigma simulation, which is the name of this file that holds the simulation, and it's going to ask us for 3 things. First, we want to put in the starting setting, and I'll just use my initials for that. Now this starting setting was what was called the indicator setting, which tells the operator what to initially set the machine to in order to decode the actual key for the true starting setting of the machine. So I enter this, and then the message key, I'll just make it my initials in reverse. and then we enter the message. And I'll just make the message, this is a test of the Enigma Machine simulator. So this will be a little long, and after we enter this in, it'll give us the permutated ciphertext based on our initial settings here. So what we've got going on, we've got the ability to completely reverse this if we know the correct initial setting and the message key, which we have. So let's go ahead and we'll decode this message. But first, to show like how it's a one-to-one transformation, we'll enter in the wrong starting settings first. So I'm going to rerun the program. And instead of using the correct starting key, I'm going to put in the wrong one first. I'm going to reverse them basically. And then I'll enter in this plain text, which was RRPX. JNFHNXNCKDIP. Quite long. Probably should have chosen a bit shorter of a message. DK. But this is roughly how tedious it was to decode something on an Enigma machine, which was still much better than alternatives. And giving it this ciphertext to decode with those settings, it gives us complete gibberish. We would expect that. So let's go ahead and try to decode the message with the correct settings. And we'll just do SCC and then CSS, or CCS rather. And then we'll enter in the actual ciphertext again, and it should give us the correct result. So you can see we've got the actual original message decoded here with X's where the spaces would have been. So we've got this is a test of the Enigma Machine simulator. And that's all there is to that. So with that done, let's actually go in and have a look at these other initial plugboard settings and other wheel settings that were used for the Enigma to produce this output. So we'll go into Vim and have a look at this setup file. And you can see up here at the beginning on line 3, we're actually constructing the Enigma machine. We've got the different rotors that we're choosing. We've chosen wheels number 2, and then wheel number 4, and then number 5. And then we've got the beta reflector here, as well as the different ring settings, which affect when the cycle of one wheel causes the next wheel to flip over. And then we've got the different plugboard associations, which usually there was a maximum of 10 associations for a total of 20 letters to be associated. And then we've got the rest of the simulation that handles the user input and giving the text back out, printing it to the screen. And this is really all that there was to it as far as the initial settings. If we were to change any of these settings here, we would actually get a very different result for our ciphertext because of how the permutations worked. So now that we know a little bit more about how the Enigma machine actually worked and what its internals were, how did the Allies break it in the war? Well, of course, due to that 84-bit key that we're dealing with, and with no computers being available, the Enigma code was essentially computationally infeasible to break with just brute force methods alone. Because of this, the Allies had to rely on certain heuristics from number theory, as well as a solid contextual knowledge of what the German communications looked like. This is something that they had plenty of information on because the Germans made several mistakes. They would oftentimes transmit messages in the same format, or they, of course, had this habit of at the very end of their messages almost always placing the text Heil Hitler or something like that, using very systematic repeated communications. And this was able to be exploited to give more clues on exactly how the Enigma machine worked on the inside. And once they figured out the wiring and how that machine actually worked, like they still had the burden of figuring out exactly what the initial settings of the machine were at any given time, at any given transmission, to be able to decode that transmission. So what are we looking at here? They started using what was called the crib system. Now, a crib in this context is just a word or a group of words that form a contiguous phrase that is expected to be present within any given plaintext in a given message. Now, the crib technique, it exploits one of the only flaws present in the Enigma Machine system, which was the fact that whenever you're pressing the keys on the Enigma Machine, if I press the A key, there is a 0% chance that the A key will then light up as a result. So, in short, no letter could ever be encoded into itself. And with that information, it was possible to drastically narrow the search space on what key you were looking for. Now, the crib system relied very heavily on the crib being accurate. That is to say, in order for it to be successful, the crib system, the cribs that were selected to be used absolutely needed to appear in the message, or else whatever analysis they were doing was completely useless. It also relies very much on having a large volume of messages that were encrypted with the very same initial settings, because the way that the Germans would structure their communications protocol, they would have for every branch, they would have a separate initial setting for the day. And this would, of course, of the day, it would change daily. So whenever the clock would strike midnight, any work that was done towards breaking the current day's settings would be completely thrown out, and you need to start over because, well, the new communications that would be coming in that would be most relevant would not contribute to breaking the old key, and it would instead be, the information you gather from the new encryptions coming in would be put toward breaking the new key. And once the key was broken for that day, every single transmission for that day could be read nearly instantly, because all that you have to do is just go in, just like a authorized receiver of the message would do, and type it into the Enigma machine, and it would give you the plain text back. Now, how did the crib system work? You would take a word, let's just say that this phrase above, right here, is my ciphertext. And I know for certain that this ciphertext contains the word test because of context, because you could always assume with a German message that it would, oftentimes end with something like Heil Hitler, but you could also make other inferences with messages that would have consistent formats, like weather reports, for example. Like there are only a very small subset of words that will ever be contained in a weather report, and the Germans always broadcasted their weather reports from very specific stations, so it was easy to pinpoint. Well, we know that this message is coming from this station, so it's probably going to be a weather report. So we're going to run all these weather report cribs against it and see if we can crack the key for the day. So, given this ciphertext we have right here, I know, because I constructed it, that it contains the word test. So what I do is I, element-wise, with the phrase, line it up against the ciphertext, and I check for instances where the letter in the ciphertext matches exactly with any of the letters in the crib. Whenever I find an instance of that, for example, this first highlighted row, we can see that this T matches up here with this T. This is what is known as a crash, and what this means is it eliminates the setting that would generate this set of text completely out of the equation. So this single crash has the potential to eliminate several settings because of how many possibilities there are. Now, and it may not seem like this is doing much. We only have 3 crashes in this instance, but like I said before, the crib system relied very heavily on volume, because every single crash would contribute something new as far as information. It would contribute new information to breaking the current day's key, and they would need thousands upon thousands of of encrypted messages to run these cribs against to be able to get the search space to be small enough to where it could be brute forced. But luckily, the Germans, obliged them and provided that very easily. And not only that, they would send the exact same messages encrypted with different settings, which would also give clues to exactly what settings were being used. Once the Enigma was broken, it had two enormous implications. One of which, one of the most immediate implications was it completely changed the tide of the war. Being able to listen in on the access, the enemy transmissions made it to where we pretty much were able to do whatever we wanted. We were able to turn the tide completely and ultimately win the war. But a secondary effect is that through researching this and through building the machines needed to break the Enigma machine, it set many of the great minds at the time on the track of actually developing general purpose computers that we know and enjoy and use today. And this was absolutely huge because before the 30s and before the 40s, it wasn't really thought that a generalized machine was even possible. But because of the contributions of minds like Alan Turing and John von Neumann, we were able to arrive at a point to where we have these general purpose machines that can do so many amazing and cool things. That's all for my presentation. I hope that you enjoyed it, and I hope you learned something new. And I hope that this inspires you to go out and do some research on the very beginnings of our discipline. Thank you so much for watching. Have a great day.